Okay, good afternoon, good morning, everybody. My presentation will be in English as the first one this afternoon. But if you have questions later on, you can ask them in Spanish. We will translate and can answer them. So after the reverse osmosis, I would like to talk a little bit about ultrafiltration, what we have done over the last, how ultrafiltration membranes have progressed in performance over the last decades. So ultrafiltration membranes have been around actually longer than reverse osmosis membranes, developed in 1935. But for the first 50 years, ultrafiltration membranes were exclusively used for very small scale applications. Filtration of pharmaceuticals was a typical application. The very first ultrafiltration plant used in large scale for drinking water was in 1988 in France. And you can still see this. It is a plant producing drinking water, but very small capacity, and even the membrane modules, 20 membrane modules of 1 square meter each, gives you a very limited capacity with a relatively large footprint. The membranes were not credited with disinfection removal, but it was just to have a small, compact, easy to operate unit to replace conventional sand filters. So what we have seen basically since the early 90s, that chlorine-resistant microorganisms were detected in some drinking water sources. These organisms could not just be removed from the drinking water with chlorine dosing, so new technologies were required. Low-pressure membranes, when tested, were very effective. Initially, microfiltration membranes were tested, the same microfiltration membranes that were used in pharmaceutical application. But what was noticed that the traditional microfiltration membranes, although they operate from a process point of view satisfactory, they did remove the cryptosporidium. They had several disadvantages. The permeability dropped very quickly. They were operated in cross-flow velocity with a very high energy consumption. And because of the small membrane surface area per membrane module, the footprint was actually pretty big. And because the limited market introduction, it was actually a pretty high-priced product. So based on this market demand, a new membrane based on this microfiltration membrane was developed, smaller pore size. Smaller pore size means the production is more stable. Pore plugging doesn't occur, so the flux is more stable. The way of operating the membrane was completely changed to dead end flow, lowering the energy consumption by a factor maybe 10. And also the footprint was reduced because membrane modules now with very large surface areas per square meter of footprint were introduced. And last but not least, obviously, cost price goes down if you go for 24/7 production. So also manufacturing technologies improved to produce more membranes in the same factory, and in this way lowering the cost of the membranes. So here are some pictures of the first generation of membranes. As you saw in one of the previous pictures, membrane modules with 1 square meter. Now we're talking about membrane modules with 35 square meters, already a lot more surface area in the same membrane module. This was realized by increasing the diameter, increasing the length of the membrane module, and by decreasing actually the size of the fiber. Pharmaceutical membranes typically have a fiber diameter of 1.5 or 2 millimeter internal diameter. With 0.8 millimeter internal diameter, you can increase the packing density by a factor 2. So not only was the physical shape of the membrane module increased, but also the packing density of membranes inside the membrane module was increased to give you even more surface area in the same footprint. To the right is one of the first plants, a drinking water plant in Holland that produces drinking water from Rhine River water that is relatively high in salinity, but also polluted with organics and with potentially some pesticides. This membrane was employed in a large number of potable water plants, but obviously improvements were always looked for. Within EXLO, we have an R&D department. The R&D department only not only improves the membrane modules, but we also look at improving performance of the system, the operating conditions of the system, modifying those to lower energy consumption or to lower chemical consumption, but also different ways of installing the membranes. So one of the first major improvements was that we increased the membrane chemistry to improve the permeability by 30%. So exactly the same physical shape of the membrane in one step could produce 30% more product flow. A very interesting side effect was that the same membrane fibers had less static charge, which means that they were easier to put inside membrane modules. So not only could we improve the performance of the membrane module per square meter of surface area, but we could also improve the packing density of the membrane modules, still with the same shape of membrane module, the same shape of the membrane fiber. So from 35 to 40 square meters, basically even retrofittable to the original plans. One of the important things for us for improving the membranes is that we always keep in mind that it is an evolution of a membrane. We don't want to have a membrane that is no longer retrofittable to membrane plants that have been installed already, that have been operated in the field. So when we design improvements, we also make sure that these improvement designs can also be used for all the plants when they go for a membrane replacement. So coming to the third generation, we did actually improve or increase the diameter of the membrane module by about 20 millimeters. This gives about 20% increase in membrane surface area. Also, the internal structure of the membrane was modified to increase the packing density by 20. And this gave us an improvement from membrane surface area per membrane module from 40 to 55 square meters. So these membranes are directly retrofittable in the previous generation vertical installed membranes. For the horizontal membranes, they're not directly retrofittable. We can improve some of the, we can translate some of the improvements to the previous generation, but not all of them. So fourth generation, here we made some improvements to the membrane fibers, internal diameter, the wall thickness of the fiber. What we also did, a detailed analysis of the packing density, how to operate our factory. So we put more automation in our membrane manufacturing to make sure that less handling means less disturbance of the fiber alignments, increasing the membrane surface area in the same membrane module from 55 to 64 square meters. So again, retrofittable to the previous generation, 15% increase in membrane surface area. On top of this, also some improvements in operation of the plant, and a major improvement for us was also a new concept of construction of membrane plants with integrated headers. You can see a picture to the right, a plant operating in Egypt, where we use the same membrane modules, but with an integrated header system to have a more compact unit that can actually be constructed on site. So now we're coming to the last improvement, the last generation of our membranes. Here we also looked at membrane fiber chemistry, but also the membrane modules. So we found out that the fiber geometry, the bundle handling, the fluid analysis allowed us to increase the membrane surface area from 64 to 75 square meters of surface area. So a very, very big step in the same physical shape of membrane modules. So still the same tube of 220 millimeters and 1.5 meters, 1500 millimeters long. You can now pack 75 square meters. If you compare this to the previous generations where you had 40, 55 square meters, you can see that we're almost doubling the amount of square meters in basically the same physical shape of membrane module.
Frans, sorry, but you have 2 minutes.
2 minutes. Yes, I'm wrapping up. This is almost the last slide.
Okay, perfect.
So
Thanks.
you have permeability quality. We analyzed as exactly the same. The permeability, because of the fiber geometry and the fluid flow analysis, we actually increased by 20%. So this brings us to the summary. We now see that it took us 50 years to get low pressure membranes accepted in large-scale water treatment applications like potable water, pre-treatment to seawater, polishing of wastewater. Over the last 25, 30 years, it went very quickly from relatively small plants for leading companies that wanted to be the first users of these plants. Now it's more or less accepted industry-wide with very large plants up to 1,000 cubic meters per day, showing exponential growth, coming to the conclusion, smaller footprints, reduction in water losses. So I didn't talk about performance enhancement, but that's also huge improvements have been made there, lower investment. Like I said, ultrafiltration is becoming the standard for water treatment, inside out 8-inch membrane filtration, rather than an alternative compared to media filters or other conventional technologies. Okay, I hope I'm just on time.